Section 3.1, Polynomial Functions and Modeling. So a polynomial function is a function of this form. That is, specifically, we just have an times some x raised to the n. These n's are just a way to line things up, this subscript, and then this is, of course, the power. Now, specifically for this polynomial function, this a sub n cannot be 0, where we technically call this leading thing the leading term because it has the highest degree. The other thing is that a sub n minus 1, all of the a sub stuff are real numbers. That will be a requirement for our polynomials. Also, each power, n minus 1, so on and so forth, all the powers have to be non-negative integers. A polynomial function is in standard form if the powers are in descending order. That is, we start with the highest power on the left, lowest power on the right. Well, once you have it in that form, the largest power piece or term is called the leading term. And then the a sub n, or whatever number is times the largest powered x, is the leading coefficient. And then n, which is the largest power, is what we call the degree of the polynomial. So just to talk about some polynomial functions, let's say I have a 0-degree polynomial. This is actually a constant function, and the graph is just a flat line. And if I were to give an example, that is p of x is equal to 4. If you have a degree 1 polynomial, that's actually called a linear function, and the graph we know looks like these slanty lines one way or the other, just not vertical. If I have a degree 2 polynomial, we call that a quadratic, and the graph is U-shaped, either facing up or down. Example, 2x squared minus 1. If I have a 3rd degree polynomial, we call that a cubic function. The graph looks like these things, upside down or not. And so example could be x cubed plus 2x minus 1. And a 4th degree polynomial is what we call a quartic polynomial, and actually looks either like a parabola or W-shaped. They could be flipped upside down, of course, but one of these two shapes or flipped upside down. For example, that could be negative 5x to the 4th plus 3x cubed. Now we want to determine which of the following are polynomial functions, and those that are, we want to state the degree, and for those that are not, we need to tell why they're not polynomials. Then we want to write each polynomial in standard form and identify the leading term and the constant. So for this first one, let's look at it. Are all of our degrees non-negative whole numbers? Well, this power is 1. This power is 4. This one's not written, but technically that's the 0th term. And so that one has a non-negative power. Alright, so that part checks out. Next question, are all of our coefficients real numbers? 6, 8, and negative 3 are all real numbers. The only non-real numbers that we really have talked about so far are I. So this thing is a polynomial function. Next question, what is its standard form? Well, if I write in standard form, that is, this thing is really 8x to the 4th plus 6x minus 3. Decreasing order of degree. Highest degree on the left, lowest degree on the right. At this point, I can just say, look, that's the leading term. This is the constant, and its degree is 4 because that's the highest power on the x's. Here I've got pi times x to the 4th plus the square root of 6. So first thing to check is, do all our variables have non-negative whole number powers? The only variable I've got is x, and it's raised to 4, which is non-negative integer, so that part checks out. Then we look at the coefficients. Are our coefficients real numbers? Pi is a real number. Square root of 6 is a real number. This is a perfectly good polynomial. Then we need to write it in decreasing order of degree or standard form, but notice that my highest degree term is on the left already, so we're done. This is then the leading term. This is then the constant. And the degree here is 4. Now for this one, step 1, look at all the variables, check the powers. X cubed, fine. X to the negative 2nd. That's not non-negative, it's negative. So right here, this is not a non-negative integer. And since that's not a non-negative integer, this is not a polynomial. Technically, this is actually a rational expression. Now, just for the sake of practice, let's check the coefficients. Square root of 10 is a real number, 5 is a real number, 1 is a real number, but it's still not a polynomial. So, p to the x, is it a polynomial? Ooh, it's got division in it, but it's divided by 17. So let's rewrite this and see if we can get it into a nice standard form. I could rewrite this as negative x cubed divided by 17 plus 3/17. And just to get it in the perfect nice standard form, that's really negative 1/17 times x cubed plus 3/17. And then we ask ourselves the question, is it a polynomial? Well, let's check the variables. X raised to 3, that's a non-negative whole number, we're good. And then negative 1/17 and 3/17 are both real numbers, so this thing is a polynomial. Specifically, this is the leading term, this is the constant, and the degree here is 3. This next one, I've got x squared plus 1 divided by x cubed minus 2. The truth is any time that we have division by a variable, if it won't reduce, it's not a polynomial. And even if it does reduce, it's not truly a polynomial because it'll have domain restriction. This right here is technically a negative, is not a non-negative whole number. So this is negative power because it's in the denominator, thus not polynomial. Then I have x raised to the 1/2 plus 1/4 x minus pi. First thing to check is our variables and our powers. X raised to the 1/2. That's not a whole number. So because that's not an integer, this thing is not a polynomial. So anytime you have radicals, you don't have a polynomial if the radical is on the variable. So the graph of every polynomial function has some common features, and so let's talk about those common features. First thing is that every polynomial function has a domain of all real numbers. That is, anything that you want to plug into a polynomial function will work as long as it's a real number. Also, polynomials are smooth. That is, they have no sharp corners or cusps. And so let me describe a sharp corner for you. Absolute value function. That point on the v, that's sharp. Polynomial functions are continuous. What do we mean by continuous? Well, it means there's no jumps, gaps, breaks, or holes. And so let's consider some things. Look at this one here. This is a polynomial function. It is smooth. It doesn't have to pick my pen up ever to keep drawing it. So that's another good way to think of continuous. Can I draw it without having to pick my pen up? Then notice that this thing has a couple problems. So here we have a corner. Then we have a cusp. So those are two problems that this thing can't be a polynomial. We have a gap, not a polynomial, and we have a hole. So these are all the types of problems you may see for not a polynomial. But if ever you have a polynomial, none of those weird things occur. When graphing polynomials, we should always think about the leading term. And the reason is that the leading term is going to feed us a lot of information. First thing is that if we know that the exponent n is increasing, that is, if you just get higher and higher powers, the trick is that between -1 and 1, it kind of flattens out. Kind of looks closer and closer to the x-axis. But then on everything outside of -1 and 1, it gets steeper. So here I want to discuss about some even degree functions. Now I want us to be careful here because specifically I'm talking about things of the form x raised to the n. These are not things that have more variables added on here. This is just x raised to an even power. That's all. No plus x's, no plus x squareds, just x raised to an even power. Now some observations that we want to make about this thing is that as long as we don't add any other stuff to it, I can guarantee that there's y-axis symmetry. Next thing is that if this thing has a positive leading term, I know that on the far left-hand side and on the far right-hand side, they're both going to be pointing up. And then if I know that that's all true, then the range of this even degree function is going to be from 0 to infinity, including 0. Now I've actually sketched this flattening in the middle just so you can recognize it and the steepness that occurs to the left and the right. Now let's change it up a little bit and let's pretend for one moment that there's a leading term and that leading term is negative. But remember, via our transformations, that just means it turns the function upside down. It reflects it across the x-axis. And so if that's the case, if we have an even degree term, then this is going to have end behavior of down on the far left and down on the far right. And if it flips upside down, then that changes the range, and you're going to go from -infinity to 0 inclusive. Now once again, remember this is strictly x raised to the nth power where n is an even number. There's no addition or subtraction anymore. For odd degree functions, let's think about something similar. Let's say that I have x raised to the n power, and n is going to be an odd number. No additions, no subtractions, just x to the nth, where n is odd. We do have some symmetry built in here. We have origin symmetry. Next thing is that if I have a positive leading term, then I can think about what happens at the ends of my graph. On the far left, it's going to be down, and on the far right, it's going to point up. The range of one of these functions is going to be all real numbers, from -infinity to +infinity. Now we didn't state the domain, but the domain of all polynomials is from -infinity to +infinity, so that's always true. Now let's pretend for one moment we change that leading term and we make it a negative number. Well, what happens? It turns it upside down. And so if it turns it upside down, then the left-hand side is going to be pointing up and the right-hand side is going to be pointing down. Now all this is going to be really useful because if I'm trying to think about what these graphs look like, knowing what happens on the far left and the far right will make it far easier to sketch these graphs. And of course the range is still going to be from negative infinity to positive infinity even if we flip it upside down. What transformation is needed to graph the function f of x is equal to 1/2 x to the fourth? Well, first thing, realize that the parent function is x to the fourth. Earlier we said that parent function x to the fourth could look one of two ways. It either looks like a W or it looks like a U shape. The only way to actually tell that is to find the zeros of the function. But for us, we're just going to say that because if we have a single term x to the fourth, I'll tell you guys that it looks like a U shape. It's a parabola. Okay. Now, this is then 1/2 times x to the fourth. But what does that do? It's a vertical compression of 1/2. And so it really gets shorter and fatter. Now, if we want to get this general shape, first off, we do know that this, we can plug in some values real quick, but these will be multiple choice on my labs. But to plug in some easy values, 0 to the fourth is 0, 0 times 1/2 is 0, so I know that 0, 0 shows up. So f of 0 equals 0. Now for the sake of argument, let's just pick something easy to plug in. F of -1. F of -1 is going to be positive 1 times 1/2 or 1/2. And then f of 1 is going to be 1 to the fourth, which is 1 times 1/2, which is 1/2. And so at -1 I get 1/2, and at 1 I get 1/2. And so I get this U shape, something like this. And that is the graph of our function, more or less. Then if I have this x to the fifth minus 8, realize that our parent is going to be x to the fifth. Well, we know that x to the fifth is in general going to look similar to x cubed or something kind of like this. It might get flatter in the middle and steeper on the outside, but that's okay. We just need to be close. Then let's discuss the other transformations occur, but this is on the outside, so this is actually going down by 8. So then I know that if I wanted to plug in values, you could. F of 0, well, 0 to the fifth is 0, minus 8 is minus 8. But this is what we already know. We know that this thing has a point there at -8. Now if I wanted to pick some other values just to kind of get my sketch right, I'd pick something a little to the right of that. How about f of 1? 1 to the fifth is 1. 1 minus 8 is going to be -7. So at 1, I get the point -7. Then for f of -1, let's plug that one in. That's going to be -1 to the fifth. That's -1 minus 8. That's really -9. And so over here I get this value. And then we just kind of fill in with the gaps with what we know. This kind of looks. Now it's not perfect, but it's just a sketch for us. You guys will have multiple choice problems, so it'll be fine. Now, what is the transformation needed to get the graph of this function? And we're going to connect the dots specifically for the correct one. So first off, parent function is going to be x to the fourth. Then, notice we have three things going on. This, and this. Well, this is up 1. This is right 1. This one does two things. It's a reflection across the x-axis or turned upside down, and a vertical stretch by a factor of 6. So then I remember that the parent function x to the fourth is either parabolic or W-shaped, but this one, because it's a single term, is parabolic. Then it gets turned upside down, so I know that it's got to be one of the upside down U-shapes. Then it moves right 1. Since it moves right 1, well, 0, 0, right 1, okay? And then it moves up 1. There's our vertex, so we know that this is it. This is the one we were looking for after those transformations. Multiplicity. Multiplicity has to do with the zeros or the roots of a function. So let's say that c, some number c, is what we call a zero or a root of a function. That is, if you plug it into the function, it's going to give you the output of 0. Then the deal is that once we know that c is a root, we have to know that x minus c is also a factor of the polynomial. This has to be true. It just is what happens because of the zero product property, right? If you factor out a polynomial completely, you set each factor equals 0. If you find whole number zeros, then that means that that binomial x minus c has a polynomial. Well, the number of times a factor shows up is going to be called its multiplicity. So let's look at an example. Here I have the polynomial of x factored out completely as x times x minus 2 quantity squared times x minus 3 quantity cubed times x plus 4. If I wanted to find the zeros of each of these things, I would set it equal to 0, and I would use the zero product property, and I would get that x equals 0. I would also get 2, 3, negative 4. Now, notice that the power on x is 1. And since it only shows up one time, then 0 is a root, and it has a multiplicity of 1. Then let's look at this one. X minus 2, zero product property says x minus 2 is equal to 0. Add 2 to both sides. I get that x is equal to 2. So I have a 0 of 2. But then, because the power on this binomial is 2, it has a multiplicity of 2. Next, x minus 3, zero product property. X minus 3 is equal to 0. I get that x is equal to positive 3. But notice that it has a power of 3, so it has a multiplicity of 3. So 3 is a root, or a 0, with multiplicity 3. Next, x plus 4 is equal to 0. Minus 4 minus 4. X is equal to negative 4. I get a 0, or a root, of negative 4. But notice that the power on it is 1. We don't write 1, but it's 1. And so this has a negative 4 root with a multiplicity of 1. Now, if anybody were to ask what's the leading term here, there's a trick. Take each of the largest pieces, the largest terms that we see, highest degree, and then raise them to each of the powers. So this is really x times x squared times x cubed times x to the first. That's really 1 plus 3 plus 2 plus 1, or 7. And so that's 1 times x to the 7th. Now, where'd that 1 leading coefficient come from? Well, there's a 1 here, and the rest of them all have 1s. If they didn't have 1s, you'd multiply whatever those numbers together, and that would give you your leading. Sometimes they'll ask you the leading term, and this is just the fastest way to find it, if it's already factored. Now, why do we care about the multiplicity of zeros? Because the multiplicity of zeros will actually help us be able to describe what the graph looks like. Specifically, let's say that we have zeros, or roots of c, and it's raised to some multiplicity m. Then the deal is that if m is an odd number, then we know that the graph is going to cross the x-axis at that value c, at that specific 0. It will cross. These are situations of crossing. By crossing, I mean I start at the negative below the x-axis and go across the x-axis. Or I start above the x-axis and I go below. That's what I mean by crossing. Now, if m is even, something interesting happens. Specifically, the graph is tangent to that point C0. That's a little weird, but we could also say that it bounces, does not cross. And so some situations of bounces are the parabola that touches the x-axis and then comes back up. That's a bouncing. That's what I mean by bounce, not crossing. Or if it's an upside down parabola, this touches the point and comes back down. So now we're going to play with this information. And we want to form a polynomial whose real zeros and degree are given. And then we're going to have to simplify our answer. And by simplify, we do mean multiply out completely. And that might be a little tricky, but we can handle it. If we know that those are our zeros, well, what happens? We need a polynomial, so let's go ahead and write it as a function. F of x is equal to a bunch of binomials. Well, remember that if c is a 0, then x minus c is a factor. And so if I have minus 3 as a 0, then I know that x minus minus 3 is a factor of the polynomial. I also know that since 3 is a 0, x minus 3 is a factor. Since 2 is a 0, x minus 2 is a factor. And since 0 is a 0, x minus 0 is a factor. So I'm going to clean this up real quick. That is x plus 3 times x minus 3 times x minus 2 times x minus 0 is just x. Now we do need a degree 4 polynomial, but notice something. Leading terms in each binomial. X times x times x times x, that's x to the 4th. So this is a degree 4 polynomial. But now to simplify it, we just multiply everything out. So let's multiply these binomials. X plus 3 times x minus 3. That's a difference of squares, so I'm going to jump straight to that's x squared minus 9. I did FOIL it and then simplify if that makes you feel better. This other one then becomes times x is x squared minus 2x. Then if I want to multiply this further, x squared times x squared is x to the 4th. X squared times minus 2x is minus 2x cubed minus 9x squared plus 18x. If we can, we should simplify further, but it won't, and I've already written it in standard form, so I'm just going to leave it as is. x to the fourth minus 2x cubed minus 9x squared plus 18x. Let's play the game again. We want to form a polynomial whose real zeros and degree are given. So we get a 0 with 3, and it has a multiplicity of 1. My polynomial then has a factor of x minus 3. And if it has a multiplicity of 1, it has a power of 1. Then I have a 0 of negative 1, which means I have a factor of x minus minus 1. And it has multiplicity 2. So I know that that binomial is squared. Now, real quick, let's think about our degree here. This is x to the first, and this is x squared. X squared times x to the first is x cubed. This is a degree 3 polynomial. So to clean it up, that is, this is x minus 3 times x plus 1, quantity squared. Then, if you want to use the perfect square trinomial formula, you could. That is x minus 3 times x plus 2x plus 1. Then I need to multiply this binomial times this trinomial. That's the double distributive property. Just to be careful here, this binomial distributes into each term. Watch out for my typo. This should be x squared. Then this is going to be x squared times x minus 3 plus 2x times x minus 3 plus 1 times x minus 3, which then gives us x cubed minus 3x squared plus 2x squared minus 6x plus x minus 3. We should clean it up as much as we can. That's going to be x cubed minus 3x plus 2x is minus x squared. Minus 6x plus x is minus 5x minus 3. That's as cleaned up as I can get it. So this is that simplified polynomial that has these properties. Now we're going to make it a little harder. We want to look at this graph and we want to construct a polynomial function that might give us this graph. So a couple things to notice. There are some zeros. Those are the roots of the polynomial. Remember that zeros and roots are just x-intercepts, here, here, and here. So really it's going to have zeros of negative 4, negative 1, and 0. Alright, great. We found our zeros. But now we have two other pieces of information that we know that we can use. That is end behavior, that's going to equal the degree of the entire polynomial, and multiplicity of zeros. So notice what happens when I get to negative 4. Well, negative 4 is a 0 with a crossing. And so that tells me that this must have an odd multiplicity. And so I'm going to use the easiest multiplicity that I can come up with just to get the most simple function for this graph. And so since this is a crossing, that means I need an odd multiplicity. And so let's say that negative 4 has a multiplicity of 1. It's pretty easy. Well, negative 1, what happens as we get to negative 1? Well, it's a crossing as well. And so it must also have an odd multiplicity, and so let's use the easiest one, 1. Then as I cross through the origin, notice that I do cross the x-axis, so once again it has an odd multiplicity, so I'm going to say it has a multiplicity of 1. Then because I have multiplicity of 1, 1, and 1, then I know the degree of this current polynomial should be 3, so we need to check and make sure that this does look like a degree 3 polynomial with the end behavior. Down on the left, up on the right, that's true. And so this is all we need. So then I can say that the polynomial that looks like this is, or could be, x minus minus 4 times x minus minus 1 times x minus 0. Multiplicities on each one of these is 1. Not necessary to write them, but it's just a good reminder. Then let's clean it up a little bit. That is, this is the polynomial of x minus 0 is just x times x plus 4 times x plus 1. And if they asked us to simplify it, we would need to multiply it all out, but I claim that this is a perfectly good possible representation for this function. So now we want to analyze the polynomial function and try to sketch the graph. And when I say sketch, I mean we just need a rough sketch. It just needs to be close enough that you could pick out from multiple choice. And so if I want to analyze this polynomial function, it's a good place to start with leading term. And so leading term, well, that's x squared times x, or x to the fourth. And so I know that this graph is actually going to behave like x to the fourth. That is, the end behavior on the far left is going to be up, and on the far right, it's also going to be up. Well, let's find the x-intercepts. Well, this is easy to find because it's already factored for us, and so we could use the zero product property. That is, x squared is equal to 0, x minus 6 is equal to 0, and x plus 6 is equal to 0. And so we get 3 x-intercepts. They are 0, 6, and negative 6. Now, notice that there are some multiplicities that occur here, and we'll get to that in a minute. Well, what about the y-intercept? Well, the y-intercept, just plug in 0 for all the x's. F of 0 is equal to 0 squared times 0 minus 6 times 0 minus 6. But honestly, the y-intercept here is just 0. So now let's talk about that multiplicity stuff we were talking about. And notice that the multiplicity just comes back to the original where we're looking for the factored forms with powers. And so the least 0 is a 0 of multiplicity 1. So when I say the least 0, let's just say that that least 0 is negative 6. And so the multiplicity is multiplicity 1. And since it has an odd multiplicity, the graph is going to cross at the x-axis at x equals negative 6. The middle 0, and I'm thinking about the number line since negative 6 is over here, and really if you wanted to graph those, you could. The middle 0 is a 0 there. It's a 0 of multiplicity 2, because remember x squared, the square part is where we got the multiplicity. And so the graph will bounce the x-axis at x equals 0. And the greatest 0 is a 0 of multiplicity 1, so 6 has a multiplicity of 1 here. And so the graph is going to cross the x-axis at x is equal to 6. Now the truth is like I said, at this point I have a pretty good idea of what this graph looks like. Not great, but a fast sketch will do. Because this graph behaves like x to the fourth, if you look at the leading term is x squared times x times x. That's just x to the fourth, and so technically I know that this is going to have some sort of up on the left, up on the right behavior. Gotta be. So up on the left, up on the right. Then since it has a 0 at negative 6, but it crosses, I know it's got to come down, cross negative 6. Well, then I know that it has to come back up to get to this next 0, but the middle 0 is a bounce, and so it's going to touch it, come back down. Then it's going to come back up through 6, but 6 has a multiplicity of 1, so it's a crossing, and then it meets back up with the end behavior. Now this is smooth, it cannot be sharp here because we know it's a polynomial. But this is that W shape we were talking about. And this isn't perfect, but it's pretty close. Let's do it again. So if I have x cubed minus 16x, first off, what does this thing behave like? Look at the leading term. It's going to behave something like x cubed. For the record, that means I know it's going to look something like this. So the end behavior on the left is going to be down, the end behavior on the right is going to be up. To find the x-intercepts, we need to set this thing equal to 0, so x cubed minus 16x is equal to 0. This is then x times x squared minus 16 is equal to 0. This is then x times x plus 4x minus 4 is equal to 0. And so then my zeros are 0, negative 4, and positive 4. And so my x-intercepts are exactly that. Negative 4, 0, positive 4. I'm going to go ahead and graph those. Negative 4, 0, and 4. What are the y-intercepts? Well, if I plug in 0 here, 0 cubed minus 16 times 0 is just 0, so the y-intercept is just 0. We've already plotted. Now, the least 0. Multiplicity is going to come from this right here, this factored form. So the least 0 is negative 4. And it has multiplicity of 1, because it has a power of 1. The graph is going to cross the x-axis there. The middle 0 is 0. It has a multiplicity of 1, because that was x to the first. It's going to cross the x-axis at x equals. The largest 0 is 4, and it has a multiplicity of 1, because x minus 4 is raised to the first power. So the graph is going to cross the x-axis at 4. Now, the only thing left to do is, what does the end behavior look like? But because this is leading term of x cubed, it's down on the left and up on the right. Then I know that it must cross this one, cross this one, cross this one. We don't have to get it perfect, we just need to be close, but I claim this has got to be close to what it looks like.